Greetings, my name is Matthew, and in this video we're going to be talking about the equation of the circle. And this is a topic that is covered in a pre-calculus class that I teach, so if you're one of my students, then I welcome you. If you're not one of my students, it's a pleasure having you. The equation of the unit circle, I think I just said the equation of a circle before. We're not going to generally talk about equations of circles. Very specifically in this video, we're going to talk about the unit circle. And if you watched my previous video titled 4.1, which links to this video, we also addressed the unit circle, and in particular we talked about the location of the radian measures as we rotate around the circle. So we're going to get a little bit more in-depth kind of coverage and explore the unit circle a little bit more today. And a big component of that is knowing these two triangles particularly well. The triangle that's on the left is an equilateral as well as an equiangular triangle, so it's a 60-60-60 triangle. And what I'm going to do is I'm going to drop an altitude. I thought there was a way to make that a straight line, but anyway, it's mostly straight. So I'm going to drop an altitude which meets the base at a right angle, and the result of that is we create a 30-60-90 triangle. So by dropping the altitude, we bisected this upper angle, making it 30 degrees, and this angle down here is still 60 degrees. And the right-hand half of this thing now is a 30-60-90 triangle. If this triangle had a hypotenuse of 2, just the right-hand half of this triangle, the 30-60-90, if it had a hypotenuse of 2, which is the long side or the side across from the 90-degree angle, the short leg of that triangle would have a measure of 1. Just because of the nature of the side lengths of a 30-60-90 triangle. The short leg is always going to be half the length of the hypotenuse. And the long leg, which is the vertical one in this particular illustration, will have a length of the square root of 3. Now, how did I get the square root of 3? I took the short leg and I multiplied it by the square root of 3. So really that square root of 3 could say 1 times the square root of 3. So maybe an even better illustration would be, let's just get rid of all of those and let's make this hypotenuse a 4. Then the short leg would have a length of 2 because that's half the hypotenuse. And the long leg would equal the short leg times the square root of 3. The Pythagorean theorem gives us that, making the long leg 2 times the square root of 3. My 3's don't come out very good with this digital pen. I don't know why that is. I'll try to exaggerate it a little. There we go. So you need to know that relationship. Even more generally speaking, a way that we depict that is to label the hypotenuse as having a length of 2x, the short leg being half of 2x, which would be 1x, and then the long leg is the short leg times the square root of 3, x root 3. All right, so please commit that to memory. We're going to be seeing those relationships very frequently. The triangle that's on the right is a 45-45-90 triangle. There's our 90-degree angle. This is 45 degrees. This angle measures 45 degrees. Now I'm going back to degrees in both of these examples because that's what you're most familiar with. 30-60-90, 45-45-90. Most of you watching this video have heard those measures before. In a geometry class, maybe. We are going to be taking these angle measures and converting them over to radians. So 30 degrees is going to be pi over 6, 60 degrees is pi over 3, 45 degrees is pi over 4, and you will come to know those relationships very well, especially if you're one of my students. We're going to be working primarily with radians. Now in the 45-45-90 triangle, if this has a hypotenuse of 2, then the legs would both measure the square root of 2. The Pythagorean theorem gives us those measures. So what's the real relationship there? If the leg had a measure of 3, then both legs would measure 3, because this is really an isosceles triangle, in addition to being a 45, 45, 90. If both legs measure 3, then the hypotenuse would measure 3 times the square root of 2. The Pythagorean theorem, again, is helping me fill in that hypotenuse length. Well, how did I get it? Other than, what's the cheat? What's the shortcut? The leg times the square root of 2 equals the hypotenuse. I'll say it again. In a 45, 45, 90 triangle, if you take the length of the leg and you multiply it by the square root of 2, you get the hypotenuse. You could do that backwards. You could take the hypotenuse and divide it by the square root of 2 and get the leg. You must be comfortable and familiar with that relationship. We're going to be doing a lot of those manipulations also. Generically, sort of, very generally speaking, I don't know why the back button erased everything I had written, but it did, so let me just manually erase those and tell you that if the leg has a length of x, then this leg must measure x, and the hypotenuse will measure the leg length times the square root of 2. All right, so that is the most general version of that relationship for the 45, 45, 90. On this page is an empty unit circle, which we will come back and work with, or we'll be drawing our own as we go along. Now, this course that I'm teaching, this Precalc class, is very much about an in-depth study of trigonometry. So here, for the first time, we are seeing sine, cosine, and tangent, and we're seeing their reciprocal functions, cosecant, secant, and cotangent. An illustration is going to be helpful for us to continue this conversation, and I'm trying to decide if I should come back up here and use, well, I don't want you to have to go onto a different page. So let's just draw a little illustration over here. Let me change this pen color, and I'm going to draw, we could even do it here. I'm going to draw the first quadrant of the XY coordinate plane, and into here I'm going to draw a very generic triangle. This is not specifically a 30, 60, 90 or a 45, 45, 90, all right? What's important about this triangle is that inside of it is an angle measure. Eventually we're going to call that a reference angle. It's inside the triangle, and it's in that angle that's really close to the origin. That's our reference angle. And across from that angle, or opposite that angle, is a side. This side right here. And since that side is across from or opposite the angle, we're going to label it opposite. Or I'll just label it OPP. Adjacent to our angle, or next to our angle, down here on the bottom, I'm going to label it ADJ for adjacent. So that's another side of our triangle that is adjacent to our angle. And the hypotenuse, of course, is across from our right angle. So we have the opposite side, the adjacent side, and the hypotenuse. Now, if I were to draw this triangle in the second quadrant, the adjacent side would actually have a negative side length because it's pointing to the left, which is in the negative x direction. But the opposite side would still be positive because it's pointing in the upward direction, the positive y direction. And we'll get into all of that later, but I just wanted to throw that at you real quick so that it's sort of in the back of your mind. All right, now, if I asked you to construct for me a fraction, I want you to build a fraction that illustrates the relationship between the opposite side length of the triangle and the length of the hypotenuse. We could do that. I could write the opposite side length, whatever it happens to be, OPP, or just a capital O, and we could divide it by the length of the hypotenuse. A faster, more efficient way for me to ask you to build the fraction that describes that relationship, that sort of ratio of those side lengths, would be to ask you for the sine of whatever the particular angle measure is. Now, what's already pre-typed into these notes for us, the angle measure is being described as using the angle measure t instead of theta or alpha or something like that. So I'm going to go back into my diagram and I'm going to change my theta to a lowercase t. I would say that it's not all that typical to use a lowercase t to describe an angle measure, but since that's what is already typed into these notes, we'll use t for a change, okay? So if I ask you for the sine of t, what I'm really asking you for, or what I'm asking you to do, is to build a fraction where the numerator is the length of the opposite side of the triangle, and the denominator is the length of the hypotenuse of the right triangle. Instead of opposite and hypotenuse, usually, and what we'll do almost exclusively, is instead of writing opposite and hypotenuse, we're just going to write O over H, opposite over hypotenuse. For cosine, what I want is the adjacent side length divided by the hypotenuse, and if I ask you for the tangent, I want the opposite side length divided by the adjacent side length. Now these other three functions, cosecant, secant, and cotangent, are reciprocal functions. So the cosecant of angle t is asking us for hypotenuse length divided by the opposite side length. Secant wants the hypotenuse divided by the adjacent side length, and cotangent wants the adjacent side length divided by the opposite side length. Don't worry, we're going to see examples where there are actually numbers of all of these things. Some of you are more familiar with sine, cosine, and tangent than others, so just be patient as we make it through these initial explanations and sort of orientations. I'm in the way up here, so let me move me over. There we go. So here we want to evaluate all 6 trig functions. I'm not going to evaluate all 6 trig functions. I'm going to evaluate sine, cosine, and tangent. And then if you want to create the other 3, it's just the reciprocal of the first 3 answers that we get. So we have to do a couple of things here. We're still using this angle measure t, so we're going to figure out what the sine of t is. But first, I'm going to go in and draw some more stuff in this diagram. What I'm going to do is, first I want to point out to you that this thing right here is the terminal side of our angle. Okay, this is a very large angle. Angle T is larger than 180 degrees. It's swung us all the way around into the 3rd quadrant. All right. Sine, cosine, and tangent, as I was describing to you at the top of this page, really pertained to the side lengths of a triangle. And I don't see a triangle in this diagram. So we need to draw in the triangle. So I'm going to go to the end of the terminal side, which I've just drawn an arrow pointing at it. I'm going to go to the end of that terminal side, and I'm going to draw a vertical side length straight up to meet with the x-axis. It's the negative side of the x-axis, but it's okay. And that's how I'm going to create my triangle. So the triangle that we're really working with is this one here. All right. I've just shaded it in a little bit. The angle measure that we're really inspecting, while t is the angle measure that swung us around into the 3rd quadrant, this is the angle that I'm really going to focus on. And you could call it t prime if you want to. That's going to be our reference angle. It's what we're really going to focus on to decide, well, where's the opposite side length and the adjacent side and the hypotenuse? All right, so let's just sort of keep our focus on that t prime. And now I want to know, well, what are the side lengths of this very unusual triangle here? Look at the coordinates of point P. The x-coordinate is negative 5/13, which means we've moved from the origin to the left 5/13. So I'm going to label that movement in the x direction as being negative 5/13. Here's where you need a really sharp pencil. Then, in order to get to point P, we moved in the downward direction, the negative y direction, a distance of 12/13. So negative tells me I'm moving in the downward direction. 12/13 is how far we moved. And so that is the length of that red side of the triangle that I drew. The hypotenuse of this triangle has a length of 1. I know that because of this over here. This radius of our circle is 1, and in fact we call it the unit circle because it's really the 1 unit circle, a circle with a radius of 1. So that's how I knew the hypotenuse was 1, or we could have done the Pythagorean theorem in order to calculate and find for ourselves that the hypotenuse is 1. So which one of these sides is which? Since T prime is the reference angle that we're focusing on, the side that's across from it is the side that has a length of negative 12/13. In other words, the side that's opposite our angle measure. So our O value is going to be negative 12/13. The side of the triangle that's next to our reference angle is the one that has a measure equal to negative 5/3. So I'll label that with a capital A for adjacent. And the hypotenuse is going to have a measure of 1. Perfect. Now we know what the O, A, and H values are. We know from moments ago that the sine function wants the opposite side length to be divided by the hypotenuse. So for this problem, we have negative 12/13 divided by 1, which is equal to negative 12/13. That 2 looked a little bit like a swan. There we go. All right, the cosine of angle T is found by taking the adjacent side length and dividing it by the hypotenuse, which here is equal to negative 5/13 divided by a hypotenuse of 1, which is equal to negative 5/13. It doesn't matter if you put the negative next to the 5, next to the fraction bar, or next to the 13. As long as there's one negative in there, you're good. The tangent function, and it is a function, is asking us to take the opposite side length and divide it by the adjacent side length. So here we have to take negative 12/13 and divide it by negative 5/13. A negative divided by a negative is going to make a positive, so the negatives will cancel out. And then, in order to simplify this, I'm going to use a technique sometimes referred to as keep, change, flip. Another way to say that is that division is the same thing as multiplication by the reciprocal. So I'm going to keep my now positive 12/13, and I'm going to multiply it by the reciprocal of my denominator, which is now a positive 13/5. So I got rid of the negatives, I canceled those out. If you want to, sort of cross those out, you can. It's up to you how you want to note that in your notes. Now I've got this multiplication problem. I kept the numerator, I changed division to multiplication, I flipped the denominator, or took the reciprocal, and now we can simplify. These 13s are going to cancel out, leaving us with a final answer of 12/5. And it's very typically okay for us to be answering all of these as fractions, even this last one, which is an improper fraction, where the numerator is larger than the denominator. Totally fine. If there's a specific request for a decimal approximation, then you can punch it into a calculator. But for now, let's just leave it. I won't actually write out all of the calculations and stuff, but let's go ahead and jot down what the other three functions are equal to. The reciprocal of the sine function is the cosecant function, CSC, of angle measure T. That's equal to hypotenuse over opposite, which in this case is equal to negative 13/12. The reciprocal of the cosine function is the secant function, SEC. Secant of angle measure t is equal to hypotenuse over adjacent, without showing any work, is equal to negative 13/5. And finally, the reciprocal of the tangent function is cotan. Let me just slide that up a little. The cotangent of angle measure t is equal to the adjacent side length divided by the opposite side length. We're for sure not going to show our work on that one. I'm all set with that. And we just take the reciprocal of the result of the tangent function. Instead of 12/5, we get 5/12. And you're doing trigonometry. Is it really that simple? It is. Other problems are going to look more complicated. This one's honestly decently complicated. I don't even really like the fact that point P has two negative measures or negative coordinates, and they're both fractions, and we had to do keep, change, flip. For where we are at this stage in the game, this is as complicated as it gets. It's going to get more complicated. It's going to look more complicated. But just because it looks more complicated, don't let that throw you. The processes are going to remain the same. I'm not going to go through all the motions on this problem. However, let's draw the triangle and label our side lengths, okay? I'm going to go to the end of my terminal side, and I'm going to draw a vertical line to the x-axis. That has helped me create my triangle. Let's label, oh, we can put in the right angle also. There you go, now it's a right triangle. Do we always draw a vertical line from the end of the terminal side of our angle to the x-axis? Yes. Always a vertical line? Yes. To the x-axis? You got it. Every time. Labeling our side lengths, point P is located at, the x-coordinate is negative 15/17, so we've moved from the origin to the left in the negative direction, 15/17. So we're actually going to label that side as having a length of negative 15/17. The negative is important. It pointed us in the negative direction, so we got to keep it with us. Then we made a turn and we went vertical. We went up 8/17. 8/17. There we go. That is the length of that vertical side that we drew in there. You see that we have angle measure T. That's the large angle that swung us all the way over into the second quadrant. However, we're going to sneak in here and we're going to label this as T prime. So even though in the previous problem I wrote that we were taking the sine of t and the cosine of t, and that's true, that really is the angle that we were taking the sine, cosine, and tangent of. But in terms of deciding where the opposite, adjacent, and hypotenuse are, that's when you want to be looking at the t prime. So let's make those decisions. The side length that is across from our reference angle is our opposite side, so we'll label that with an O. The side length that is next to or adjacent to our reference angle is called the adjacent side, so we'll label that with a capital A. We're working with the 1 unit circle again, so I know that my hypotenuse is going to measure 1, so we'll make that look like a 1 and we'll label it with a capital H. You can now go through the same motions as you did in the previous problem in order to calculate sine, cosine, tangent, and then flip the three of them in order to get your reciprocal functions. What else do we have? All right, let's go down here. Evaluate the trigonometric function at the given angle, or state that the expression is undefined. Now they're not giving us a picture of the angle. They're just telling us what the angle is. For my students, which are the majority of people watching this video, I think, these are going to be the style of questions that I give you on your speed quiz. All right, so let me show you what this first one looks like. This says the sine of pi over 6. Here's what I want y'all to be able to do. I want you to look at the pi over 6 and immediately know where that is on the unit circle. All right, in the previous video, and in class, we went around and we labeled all of the locations on the unit circle with the radian measures. So I see pi over 6. I know it's in the first quadrant, so I'm going to sketch myself the first quadrant. I know that pi over 6 is a third of the way up into the first quadrant, roughly there. On the unit circle, you know, if we actually drew in the circle, which I don't want you to do, and we cut the unit circle, or we cut the first quadrant into thirds, all right, maybe I'm a little low, but it's pretty close. I can just hit the back button and redraw it, which is a nice option. All right, a little bit higher. And that's the terminal side of my angle measure. Really, this angle right here measures pi over 6, which is 30 degrees. But we put our little label out here, pi over 6. Now, since that's the terminal side of my angle, I'm going to go out to the end of it, and I'm going to drop myself the vertical leg that comes down and meets the x-axis. I can put my little right angle mark in there, and I've got myself a right triangle. I know that pi over 6 is 30 degrees. Therefore, this is a 30, 60, 90 triangle. This is really pi over 6, which is 30 degrees. And this is 90 degrees. Therefore, this is 60 degrees. So it's a 30, 60, 90 triangle. We could label the hypotenuse as having a length of 1. I'm not going to do that. I'm almost never going to do that. I'm going to label the hypotenuse as having a length of 2. You could pick any even number you want to, and this will play out very nicely. I labeled it with a 2 so that when I label the short leg of my triangle, it will have a length of 1. Because I know from our conversation about the 30, 60, 90 triangle that if I take the hypotenuse of a 30, 60, 90 triangle and I cut it in half, that's the length of the short leg. The long leg will equal the short leg times root 3. So this leg measures the square root of 3. The 1 is opposite or across from my angle measure, so this is my opposite side length. The square root of 3 is next to my angle measure of pi over 6, so that is my adjacent side length. Surely the 2 is equal to my hypotenuse, so equals h. And then I'm going to come over here and remind myself that the sine of an angle measure, in this case pi over 6, is equal to the opposite side length divided by the hypotenuse. And in this problem, the opposite side length has a measure of 1 and the hypotenuse has a measure of 2. And so that's the sine of pi over 6. Let's do another one. Cosecant 7 pi over 6. 7 pi over 6, where's that? Let's see if I can do this. Is that correct facing you? Yeah, because it's mirrored. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6 goes horizontal, aiming in the direction of the negative x-axis. 7 pi over 6 is one click down from there. So I'm high in the third quadrant. I'm up here. And then I'm going to draw my vertical side length, which makes the right angle with my x-axis. Now, look at this. This is 7 pi over 6. That amount of rotation is 7 pi over 6, which is why we could, if we wanted to, we could label this as being 7 pi over 6 down here. I don't care about that labeling of the 7 pi over 6 all that much, but let's put it there for the moment. Also, due west is the same thing as 6 pi over 6, which is pi. What's the difference between 6 pi over 6 and 7 pi over 6? please say pi over 6. Did you say pi over 6? All right, so the difference between 7 pi over 6 and 6 pi over 6 is pi over 6. I'm asking you that because I want to know the size of this reference angle right here. And I'm telling you that that is pi over 6, because the difference between 6 pi over 6 and 7 pi over 6 is pi over 6. So that's the size of that little reference angle in there. Who cares? You do, because pi over 6 is the same thing as 30 degrees, which means we're working with another 30, 60, 90 triangle. Pi over 6 is 30 degrees. I'm going to label my hypotenuse with a 2, which means that my short leg has a measure that's half of that, so that's a 1. The adjacent side length, or the long leg in this case, is going to measure the square root of 3. Okay, hypotenuse is 2. I choose to use a hypotenuse of 2. We could do it with a 1, but if this was a 1, then this would be a 1/2, and this would be the square root of 3 over 2. I say, nay, I don't want to do it that way. So I just double everything, and then I don't have to worry about it having any denominators. All right, so that's why I do that. It's why I use a hypotenuse of 2. So the hypotenuse is 2. The short leg of our 30, 60, 90 triangle is half of that, which makes it a 1. I take the short leg, I multiply it by the square root of 3. I get the long leg, which is the square root of 3. I wrote that in. Now, be careful, because this is the origin right here, which means in order to get out to this point right here, we had to go to the left the square root of 3. And moving left is a negative movement. So I'm going to make this negative square root of 3. And once I made that movement of negative square root of 3, then I had to go down. And down is a negative movement. So we're going to label this 1 with a negative sign and make it a negative 1. The coordinates of this point right here are negative square root of 3, comma, negative 1. Because we went left root 3 and down 1. So those are the xy coordinates of that point. The side length that's across from our angle measure is the negative 1, so we could label that with an O. The side length that's next to our reference angle is the negative root 3, so we could label that with a capital A. The hypotenuse is the 2. We've got our O, A, and H. Now, what in the world is cosecant? The cosecant of 7 pi over 6 is, cosecant is the reciprocal of the sine function. So it's hypotenuse over opposite. Cosecant is the reciprocal of the sine function, so it's hypotenuse over opposite. Should you commit that to memory? You should. We know what the hypotenuse is. It's 2. We know what the opposite side length is. It's negative 1. So our final answer is 2 divided by negative 1 is negative 2. Again, these are the style of question that I'm going to ask on the speed quiz. How much of this work do I want you to show when you complete the speed quiz? I want this diagram. I want the x-axis, the y-axis, the hypotenuse, the vertical leg. I want you to also show the... Oh, I'm getting a little pop-up at the top of the screen. Sorry about that. I also want you to label the side lengths, all 3 of them. You can put the A, O, and H with them if you want to. And then I want to see all of this. I'm going to give you 5 problems like this. And I want you to create all of that information, including a right answer for all 5 problems. I want you to do all 5 of them correctly in 9 minutes. That's how important this is. This is the foundation for multiple chapters worth of material that I'm going to be covering in this class, and hours worth of work and stuff that we're going to see in these videos. So you've got to be able to do this very well, pretty quickly, and extremely accurately. Cosine of 2 pi over 3. 2 pi over 3 I know is in the second quadrant. It's not 3 pi over 3, it's 2 pi over 3. So it's high in the second quadrant. I'll drop my vertical leg so that it's perpendicular to the x-axis. I'll use a hypotenuse of 2. I know that this angle measure is 2 pi over 3, which means that my reference angle in here excuse me, is pi over 3. Pi over 3 is 2 pi over 6's, which means it's 2 30 degrees, which means it's 60 degrees. That's a bad place to label that, but I'm leaving it there. So that's 60 degrees. I bet I could actually fit it inside of here. Is 60 degrees, which means that this up here must be our 30-degree angle, which means that this is my short leg, which is half of my hypotenuse. So I'm going to label that with a 1. But it's to the left of the origin, which means it must be a negative 1. Now the long leg of the 30, 60, 90 triangle is the short leg times rad 3. So this is equal to the square root of 3 up here. But it's in the vertical direction, the upward direction, which is a positive direction. So I'm going to leave it as a positive rad 3. Across from my angle measure is my opposite side. Next to my angle measure is my adjacent side. My hypotenuse is my hypotenuse. Cosine is, cosine of 2 pi over 3. Cosine is adjacent over hypotenuse, which in this case is negative 1 over 2. Don't have to simplify that. That's just my final answer. You could go back and time me and see how long it took to do that, including the articulation and maybe a little bit of extra labeling. That's what I need you to be able to do. You got to be able to do those quickly, accurately. Nice diagram, just quick bit of an illustration that you understand what you're doing and what the relationship is for the function that you're working with, and then a final answer in a box. I went through those quickly. You should go back, redo those, go to the original problem, pause it, try to do it yourself, then watch me work through it with all of the explanation and stuff. Find as many examples of this as you can. Just start doing these until they're easy. Okay, that's where you need to be. Properties of trig functions. Domain and range. Remember that domain is input, range is output. Like x is the input, y is the output. Into the sine function, you can put anything you want. From negative infinity to positive infinity. Into the cosine function, you can put anything you want. From negative infinity up to positive infinity. When we graph the sine and cosine function, they're going to look like waves. And they're going to go all the way to the left and all the way to the right, forever and ever, from negative to positive infinity. Now the range, the output values, are only going to go from negative 1 to positive 1. And I'm including those values using square brackets. Same thing for the cosine function. It's a wave that has a maximum y value of 1 and a minimum y value of negative 1. So it's going to be wedged in between, it's going to be confined, okay, vertically. We'll see those later. And they're very important, and they're going to be important when we start working with inverse trigonometric functions. The domain and the range, and they're going to trade places just like x and y used to trade places in an algebra class when you found the inverse of a function. Now, even and odd. I think we talked about these briefly in the previous section. If not, let me remind you, a function is even if there's sort of a test that we can do. If f of x is equal to f of negative x. For example, if f of x equals x squared, notice f of 3 is equal to 9, and f of negative 3 is also equal to 9. Ooh. Okay, so our x values in that example are 3 and negative 3, or the inputs are 3 and negative 3, and the outputs are both 9. This is the 9. This is the 9. This is the 3. This is the 3 being negated. Okay? So that's how you can tell if a function is even. If every time you negate an input value, the output doesn't change. And a function is odd if f of negative x is equal to negative f of positive x. What that means is that if you use an opposite input value, you get out an opposite output value. For example, if f of x equals x to the third power, notice f of 2 is equal to 8, but f of negative 2 is equal to negative 8. If you negate the input, you get an opposite output value. The positive 8 became a negative 8. All right, so just some quick examples of even and odd functions. Which of these functions are even functions? As far as the trig functions we've been talking about so far, the cosine function and its reciprocal function secant, S-E-C, are even functions. The odd functions are sine, its reciprocal function cosecant, the tangent function, and its reciprocal function cotan are odd functions. I'm just giving you pieces of the puzzle and not really telling you where they fit. I'm giving you tools and not really showing you how to use them or when you use them, what happens. We'll get there. Just, it's not lost on me that I'm just sort of blowing through this stuff, okay? Here we go. We get to see them in action. Evaluate the trig function and then use even and odd properties to evaluate part B. So what's the cosine of pi over 3? Here's another great opportunity for us to practice a speed quiz question. The cosine of pi over 3 is, give me just one moment. Sorry, there was a little background noise there. Okay, so speed quiz, cosine of pi over 3. Where is pi over 3? It's 2 pi over 6s, so it's high in the first quadrant. So let's draw the first quadrant. We're pretty far up there. I'll drop my altitude so that it's perpendicular to the x-axis. I've done this enough times now that I know that pi over 3, when I'm that high in the first quadrant, this reference angle must be 60 degrees. So however you want to label that in your notes. That angle, the reference angle, is pi over 3, which is also 60 degrees, makes this a 30, 60, 90 triangle. So that's the 60. This is the 30 that's up here, and your 90 is obvious. I like to use the hypotenuse of 2. The short leg, which is across from the 30, is equal to 1. The long leg, short leg times rad 3, makes it a rad 3. And none of those need to be negative because the 1 is in the positive x direction. The root 3 is in the positive y direction. Oh, the hypotenuse will always be positive, by the way. Cosine of pi over 3 is equal to, cosine is adjacent over hypotenuse. My adjacent side is next to my reference angle. My opposite side is across from my reference angle. My hypotenuse is my hypotenuse. So I've got an adjacent of 1 and a hypotenuse of 2. Nice, so that's the cosine of pi over 3. What's the cosine of negative pi over 3? Well, cosine is even, therefore the cosine of pi over 3 is equal to the cosine of negative pi over 3. And the cosine of pi over 3 was equal to 1/2, therefore the cosine of negative pi over 3 is also equal to 1/2. For an even function, if you negate the input, the output doesn't change. It's still positive 1/2. Ah, good. More practice. The sine of 2 pi over 3. We've already worked with 2 pi over 3, didn't we? I think we did. Let's use, let's do a pi over 4. Yeah, that's not going to hurt anybody. Let's make this, scribble out the 2, maybe, and let's change this to a 4, and scribble out this 2, and let's change this to a 4. There we go. All right, so what's the sine of pi over 4? Where's pi over 4? It's halfway up the first quadrant. So I'm drawing the first quadrant. I'm going halfway up. I'm dropping my altitude so that it's perpendicular to the x-axis. I'm still using a hypotenuse of 2 because I get to choose that. In a 45, 45, 90 triangle, which this is, because my reference angle right here is pi over 4. And pi over 4 is equivalent to 45 degrees. So that's a 45, which means this is a 45. We know where the 90 is, which means I can take my hypotenuse, divide it by the square root of 2, which gives me a leg of square root of 2 and a leg of square root of 2. These two legs are the same because the angle measures across from them are the same. Neither one of the root 2's need to be negative because we're in the first quadrant, and so we can evaluate. The sine of pi over 4 is equal to, sine is opposite over hypotenuse, which is equal to the square root of 2 over 2. Done. Now, what about the sine of negative pi over 4? The sine of negative pi over 4, well, sine is odd, I should have written first. Sine is odd. Therefore, the sine of negative pi over 4 is equal to negative sine positive pi over 4, based on that little test that we talked about at the top of the previous page, I think it was, when we were talking about even and odd functions. Well, I know that the sine of pi over 4 is equal to the square root of 2 over 2. Therefore, the sine of negative pi over 4 is equal to negative square root 2 over 2. We negated the input, therefore we must negate the output. Why? Because we're working with an odd function. The sine function is an odd function, so if you negate the input, you will get out the opposite output. Sine of positive pi over 4 was positive root 2 over 2. Sine of negative pi over 4 becomes negative root 2 over 2. Again, that's a feature of an odd function. Period properties. I can't believe we're only on page 7. There's a lot of information. This stuff's dense. And I know that my explanations can be maybe overly thorough sometimes, so I apologize. Hopefully you're watching this at like 1.5 speed, so that you can move through it a little more quickly. All right, a function f is periodic if there exists a positive number p such that, right, so what's happening is we're adding something to the input into our function, and we're getting out a y value that we've seen before. This is a y value. This is a y value, and we're being told that those two y values are equal to each other. But the input the input values are different. That one says t plus p, and the other one says just t, and the output values are the same? Yeah. And if that happens consistently, thanks to this p value, then we're working with a periodic function. All of these trig functions are periodic. So it's a good thing we're talking about this. The p value that gets added in there is called the period. Some of our functions have a period of 2 pi, and some of them have a period of pi. So let's fill in this little table here. The sine function and its reciprocal function, cosecant, cosine and its reciprocal function, secant, are all 2 pi periodic or have a period of 2 pi. The tangent function and its reciprocal function, cotan, are pi periodic. Use the trig function to, evaluate the trig function. Oh, good. Oh, cotan of pi over 2. That's not good. We don't want to do that. Pi over 2 is due north, and it's very difficult to diagram, so we're going to do that later once we've talked about the graphs of these 3 functions. So let's change this problem. Instead of pi over 2, let's use, I'd like to stay in the first quadrant though. Let's use pi over 3, I suppose. And then we'll change this down here, will also be over 3. 15 pi over 3? That's kind of weird. Let's make it, all right, I'm going to pause because I have to actually think for a second, and it might take more than a second. Okay, I made it look like a second. We're going to change this to be 10 pi over 3. There we go. All right, cotan of pi over 3. Pi over 3, where's pi over 3? Well, that's 2 pi over 6s, so that's high in the first quadrant. So I'm drawing the first quadrant. See how if you do enough of these, it can end up going really quickly? Because you're going to find that you're drawing the same diagrams over and over again. But that's only if you draw a whole bunch of diagrams, that you're going to see the same ones repeatedly. So we're high in the first quadrant. There's our right angle. My reference angle is the pi over 3, which is 60 degrees. My hypotenuse is 2. My short leg is 1. The long leg is root 3 because the root 3 is across from the 60, and the 1 is across from the 30 degrees. And cotan of pi over 3, cotan, let's see, tangent was opposite over adjacent, so this must be adjacent over opposite. Better make that look like an A. There we go. And the adjacent side length is the one that's next to my reference angle. The opposite side length is across from my reference angle. The hypotenuse is the hypotenuse. So A is a 1, and O is the square root of 3. Nice. We could even rationalize this denominator and say that it's equal to 1 over the square root of 3 times the square root of 3 over the square root of 3. That's how we rationalize a denominator, if you didn't remember. So that's equal to the square root of 3 over the square root of 9, which is 3. So root 3 over 3 is the cotan of pi over 3. Root 3, I don't know why the 3's don't come out nicer with this digital pen, but anyway, root 3 over 3. So what's the cotan of 10 pi over 3? So here's what I want to show you, is that the cotan of 10 pi over 3 is equal to the cotan of pi over 3 plus 3 pi over 3 plus 3 pi over 3 plus 3 pi over 3 for a total of 10 pi's over 3. Now, this is equal to pi, and this is equal to pi, and this is equal to pi. That was a very bad pi. Bad pi. We took the initial angle of pi over 3 and we added pi to it 3 times. I don't care if it's 3 times or 67 times or 2 times or negative 17 times or negative 1,000 times. We're adding in multiples of pi. And cotangent, as we put in our table at the top right corner there, cotan has a period of pi. And no matter how many times you add in the period of the function, the output value will not change. You can add or subtract it a whole slew of times, and the output's not going to change. So this is still equal to the square root of 3 over 3. you need to write into your notes some sort of articulation. You need to articulate that logic that's going to make sense to you. Rewind it and listen to the way that I described it. I'll try to describe it a different way again the next time we talk about it. But again, no matter how many times you add or subtract the period into the input of the function, the output value is not going to change. Cosine 3 pi over 4. 0 pi over 4 is 1 pi over 4, 2 pi over 4, 3 pi over 4. We're halfway into the second quadrant, so I'm only going to draw the second quadrant. I'm halfway into it. I drop my altitude. There's my right angle. This is the 3 pi over 4, but my reference angle is only 1 pi over 4. 3 pi over 4, 4 pi over 4 means that this is a 1 pi over 4. So my reference angle is a 45-degree angle, which makes this a 45, 45, 90 triangle. And then I'm going to label my hypotenuse with a 2, because that's how I like it, which makes my legs the square root of 2 and the square root of 2, except the leg that's on the bottom is moving in the negative x direction. We started at the origin and we moved to the left. All right, so that needs to be labeled with a negative because we moved in the negative horizontal direction. This moved in the positive vertical direction, so that can stay positive. The side that is next to my reference angle is my adjacent side. The side that is across from my reference angle is my opposite side. The hypotenuse is the hypotenuse. We know what all of our sides are now. The cosine of 3 pi over 4 is equal to, cosine is adjacent over hypotenuse, which here is negative square root of 2 over 2, which cannot be simplified, so that's our answer. The cosine of 11 pi over 4 is equal to the cosine of, I'm hoping it's 3 pi over 4 plus whatever the period of the cosine function is. And the period of the cosine function is 2 pi, says right here. So, can we really take 3 pi over 4 and add 2 pi? Sure can. 2 pi is the same thing as 8 pi over 4. So we've added, that's an arrow, 2 pi, which means our output value is not going to change. It's still equal to negative root 2 over 2. Also realize that if you rotate, I hate that this is mirrored, I need to change that. There you go. If you start out aiming at 0 and you rotate up to 3 pi over 4, and then you rotate another 2 pi, you're rotating another full rotation. You're just going all the way around, back up to the middle of that second quadrant again. On the diagram, you've rotated up to 3 pi over 4, and then you're just going all the way around another 2 pi. It lands you in the same place, halfway into the, there we go, halfway into the second quadrant. So it should be no surprise that the answer to those two questions is the same. Find the exact value without a calculator. The sine function has a period of 2 pi. That piece of information allows me to say that my original statement is equal to the sine of simply negative pi over 4. Why? Because if we start at negative pi over 4 and then we rotate negative 2,000 pi radians, Well, we're rotating in the negative direction because it says negative 2000 pi. And what's 2000 pi? It's 1,000 full rotations in the negative direction. I don't really care that it's in the negative direction. If I spin around in my chair to the left, or if I spin around in my chair to the right, as long as I go all the way around, I'm going to end up here with you again, right? I do that 1,000 times. For one, I'm going to puke. And for two, well, all right, I need to go back and erase that. Anyway, 1,000 full rotations is what's key for you to understand there. It's also 1,000 periods of the sine function. And so the output is not going to change as a result of subtracting 1,000 full rotations or 1,000 periods of the sine function. Now we need to evaluate the sine of negative pi over 4. There's a couple of ways we could do that. We could draw our diagram having dropped pi over 4 down into the fourth quadrant. So we could draw the diagram in the fourth quadrant, or remember that sine is an odd function. Therefore, we can rewrite this statement as equaling negative sine positive pi over 4. It looks a lot like we just took the negative sign out of the function and plunked it down in front of the function. Visually, it looks like that's what happened. But what really happened is we're using the property of the fact that the sine function is an odd function. Okay, now we need to evaluate the sine of pi over 4. You should draw yourself a diagram and go through the motions and label all your things. And if you do that, opposite over hypotenuse, opposite over hypotenuse is going to equal the square root of 2 over 2. But this negative sign comes down, making our final answer negative square root of 2 over 2. That negative sign is that negative sign. There you go. Sweet. What else we got? Fundamental identities, the reciprocal identities. There are no reciprocal identities written right here. We already talked about the fact that sine has a reciprocal function, which is cosecant. Remember that the reciprocal of 2/3 is 3/2. Also remember that the reciprocal of 5 is 1/5. So the reciprocal of sine is 1 over sine. I'm going to use theta instead of t. The reciprocal of the sine function is cosecant, theta. The reciprocal of cosine is secant. And the reciprocal of the tangent function is cotan. Can I take the reciprocal of reciprocal? Absolutely. 1 over cosecant would equal the sine function. And if you'd like to fill those in, we can. It's the reciprocal of the reciprocal. I need a little music in the background or something. It's just dead air, and it's causing me to make mistakes. There we go. 1 over cotan is equal to tangent. Notice every time I wrote one of those functions, I put a theta after it. There either needs to be a variable or a number after one of those functions. You don't ever just see the square root function floating around out here without a number or a variable under it. You don't see a square, right, a little exponent of 2 without some kind of an argument here. There needs to be an argument here, Logarithms. You have to take the log of something, square root of something. I better be cubing something. You better be taking the sine of something. Okay, all of these trig functions need to have an argument. Whew. Is that really only page 9? Wow, so much to learn. Quotient identities. The quotient identities tell us that the sine of an angle measure divided by the cosine of an angle measure is equivalent to simply taking the tangent of that same angle measure. You can also take the reciprocal of both sides of that equation, which tells us that the cosine of theta divided by the sine of whatever the angle measure is equal to the cotangent of theta. Reciprocal of tangent is cotangent. And then there are the Pythagorean identities. I could turn this video into like 7 videos. I should really do that. The Pythagorean identities are super important. You don't see them a ton, but when you do see them, it's very gratifying. You're like, hey, I know what that is. Especially when it's one of the modified versions of the Pythagorean identity. So, similar to a squared plus b squared equals c squared, or the equation of the unit circle, which is x squared plus y squared equals 1, the first Pythagorean identity is sine squared theta plus cosine squared theta equals 1. Sine squared plus cosine squared equals 1. There are 2 other versions of this equation. If you take the entire equation and divide it by sine squared divided by sine squared equals 1. Cosine squared over sine squared equals cotangent squared. And 1 divided by sine squared equals cosecant squared theta. So that's version number 2. In order to create version number 3, if you take the first version and divide it by cosine squared, you'll get the third version. So sine squared divided by cosine squared equals tangent squared theta. Cosine squared divided by cosine squared equals 1. And 1 divided by cosine squared equals secant squared theta. You can, if you want to, memorize all 3 of those, or just memorize the first one and know how to derive the other 2. Use identities to evaluate the following functions. So, the tangent of t is equal to the sine of t divided by the cosine of t. And this problem tells us that the sine of t is equal to 2/3, and the cosine of t is equal to the square root of 5 over 3. And if we use keep change flip, we can write this as 2/3 times 3 over the square root of 5. The 3's cancel, leaving us with 2 over, it's not much of a 2, over the square root of 5. And if we multiply by root 5 over root 5, we get 2 times the square root of 5 divided by 5. I'm getting tired and a little shaky. 2 root 5 over 5. So that would be our final answer there. So the fact that I took tangent and wrote it as sine over cosine, that's using the one of the quotient identities. Cosecant is the reciprocal of the sine function. So the cosecant of t is equal to 1 over the sine of t, and we know what the sine of t is. It's 2/3. And when I do 1 over, essentially I'm taking the reciprocal. So the reciprocal of 2/3 is 3/2. I would not have done it that way. I would have simply recognized that I'm being asked for the cosecant, and I would have thought to myself, cosecant, Well, that's the reciprocal of the sine function. I know what the sine function is. It's 2/3. So I'll take the reciprocal of 2/3 and get 3/2. I never would have picked up my pencil. I would have done that in my head and gone right to 3/2. There's potential for you to get there, okay? Don't shake your head like that and think, well, I can't do that. I'm never going to be like that. You can do it. Secant is the reciprocal of the cosine function. Cosine of t is √5/3. So secant's going to be 3/√5. Which you can rationalize the denominator if you want to and write it as 3√5/5. And cotangent is the reciprocal of the tangent function. We already figured out what the tangent function is. Take the reciprocal of it, and you're there. Don't take the reciprocal of this, though. Take the reciprocal of this. Just go immediately to √5/2. Use the Pythagorean identity to find the cosine of t. Tricky. What's the Pythagorean identity? Sine squared, well, we'll use t, plus cosine squared t equals 1. I don't know what sine squared is. Sine squared is the same thing as taking the sine of t and squaring it, which means we have to take the square root of 21/5 and square it, which is equal to 21/25. So sine squared t is equal to 21/25. So we've got 21/25 plus cosine squared t is equal to 1. I'm going to have to do subtraction here. So I'm going to take the number 1 and I'm going to write it as 25/25 so that I'm already set up with a common denominator. Now I'm going to subtract 21/25 from both sides. I could put a little note over here that I'm subtracting 21/25 from both sides, which leaves me with 4/25 on the right-hand side. And now I'm going to take the square root of both sides. Of course, right after I finished saying, well, you never see a square root symbol just floating around empty like that, but this is me just taking a note. I'm not actually doing any of the math over here. But on the left-hand side, the square root of cosine squared is just cosine t, and the square root of 4 is 2, and the square root of 5 is 5. And we have figured out the cosine of t. It's 2/5. That's kind of cool. You can go through similar motions in order to determine the, right, we're being given a different value for the sine function. So you have to replace your √21/5s with a 7/8. That's 49/64. Those numbers are not going to be so nice. You're going to end up with a radical in your final answer. 64, 49. I'm not very good with arithmetic. I think the difference there is 15. So maybe you're going to have like √15/8, something like that. Give it a shot, see what you get. If you're one of my students and you're not so sure that you got the right answer, you can ask me in class. If you're not one of my students, get an answer and then take the inverse sine of 7/8 on a calculator and see what you get. I suppose that's another option. And here are some calculator problems. We're not going to do those. All right, I thought I was going to make 2 videos in one sitting, but we've been at it for 1 hour and 15 minutes. We are amazing. Can't believe we worked for that long. We're so strong. Hey, thanks so much for being with me. That was a long haul. A lot of good stuff in there. I'm going to do my best to timestamp this video as soon as possible. But first, I'm going to go get something to eat. Thanks, y'all. See you again soon.